Okay, hi everyone. My name is Julissa Rodriguez, and I will be doing my presentation on myotonic dystrophy type 1, or mostly known as Steinhardt disease. The reason for it being named Steinhardt disease is because it was named after the German scientist who wrote the paper of it in 1909. And so myotonic dystrophy has two types, and in this presentation, we'll be focusing on the cellular processing of myotonic dystrophy type 1, or abbreviated as DM1. Jumping right in, DM1 is a group of genetic disorders affecting multiple systems such as the skeletal and muscle system, as well as the endocrine and nervous system. From the effects of a mutational expansion on the genome, we can further simplify the genetic disorder into three categories, depending on how large the expansion is. These can be summarized into mild, classical, and congenital. These categories are based on the mutational repeats occurring in the expansion. People who experience mild generally can live life normally, but those who experience classical will endure symptoms more severely. For the purpose of this presentation, we'll be focusing on classical DM1. Those who experience congenital, it's usually infants who are born with a high number of tandem repeats in the expansion and don't really survive that much longer once they are born. The main symptoms of classical DM1 is that these patients will experience myotonia, which is described as the inability to relax the muscles after voluntary contraction at will. They will also experience distal muscle weakness and muscle wasting at the front arms and lower legs. This is where muscle shrinks and loses their mass. This results in the physical appearance of droopy eyes and also droopy face with a hollowed appearance of the cheekbones. Patients will also show problems in the eyes with cataracts and even abnormalities in the heart. They will have shorter lifespans depending on the range of the severity of the mutation in the gene, but diseases often show more symptoms with age. The rarity of the disease is between 1 to 8,000 and between 1 to 8,000 and 20,000, and that depends on what country you live in. It is most prevalent with patients of European descent. Moving on to gene locus, DM1 is an autosomal dominant heritable disorder that affects the gene DMPK, and DMPK will produce myotonic dystrophy protein kinase protein. This gene is placed on the non-coding region of the long arm of chromosome 19, and since it is an autosomal dominant mutation, this means that with one copy of the gene, that is good enough to cause a disease. The non-coding region is translated into mRNA, but not into the protein. And here in the figure below, you can see that the DMPK gene is on the non-coding region. And here you can see the tandem repeats of CTG, cytosine, thymine, and guanine. The classical DM1 disorder will have a repeat of 100 to 1,000 on the non-coding region. Moving on to gene product and role in the cell, the proper role of DMPK is to be able to produce the myotonic dystrophy protein kinase protein, but this is involved mainly in muscle cell communication and heart and brain cell communication. Other functions of the DMPK gene include skeletal muscle structure and function of the of cardiac conduction and heart contraction. It also affects calcium and sodium ion transport and homeostasis, synapse structural plasticity, intracellular signal transduction, phosphorylation of proteins, insulin regulation, and many other cell signaling processes. So mutational result on the gene product, the overexpansion of the CTG repeats causes hair loop-ins to occur between these bases. And when translating, gene expression stops and the product of the protein cannot be generated. Without translation of mRNA, the intron that has been expanded causes dysfunction in the protein synthesis and misregulation and expression. Here are the figures below. You can see that the double hairpin loop is forming. Recruitment of the CUG and binding protein causes formation of the nuclear foci. This causes alternative splicing and misregulation of these two main enzymes, which has disturbance of gene expression between all of these enzymes. Here you can see this is the normal cell regulation, and this is a person with DM1. How molecular genetic mutation results to the pathology. The main effect of the mutation on the DMBK gene is that myotonic dystrophy protein kinase loses much of its cellular activity and protein functioning. This results in the disturbance of a cascade of enzyme functioning, starting off with the MYPT or myosin phosphatase enzyme. Here you can see this is what I'm talking about. This is what mainly causes the myotonia and like the inability to relax after voluntary muscle contraction. CUG and BP binds to the trinucleotide repeats after the loss of the DMPK activity. This causes the alterations of the mRNA processing. PLN accumulation causes myotonia. Here you can see right here. Intracellular dysfunction in the cycling of calcium and sodium ion change causes the cardiovascular diseases. And other genes affected are like the SIX5, which causes the functioning of the eye. This will mainly affect the cataracts. There's also problems with the insulin receptor gene, the cardiac tropinoin T gene, which affects the contracting of the heart muscle. As for treatment, there is not much we can do when it comes to myotonic dystrophy type 1. However, there are ways to manage occurring symptoms which could minimize the disability. You could also go to genetic counseling to refer and see if you have starting heart disease. And you should also be monitoring your symptoms of your heart disease and neuromuscular diseases. As I said earlier, this is an autosomal dominant trait, which is passed on with just one copy of the gene. But as there's more mutation and more tandem repeats with the gene, as you pass it down, it is more likely for anyone who gets it after to have more repeats, which also causes more severity of symptoms. Other methods to help current patients with DM1 is also by doing gene therapy, where you can see in these 4 squares below, you can look at degradation, where you splice out the mutant RNA, neutralization, missplicing reversal, and exon skipping. New innovation with bioengineering CRISPR insertion. You can do gene editing therapy. That is with repeat excision, pass insertion, DCAS9 repeat blocking, and direct RNA targeting. As for that is my presentation. My references are here on the right, and thank you for your time.